Good day all, this is Professor Friday coming at you one more time. Today we are going to be doing a little bit of fancy factoring. So we are given that negative 3 minus I is a root of f of x equals x to the fourth plus 4x cubed plus 3x squared plus 10x plus 50. And we're going to factor the polynomial completely. So something I'd like to point out first. Anytime it comes to these factoring problems, there is a strong correlation between roots and factors, and we're going to be taking full advantage of that. If r is a root, then x minus r is a factor. That's one of the big things that we do throughout this process. Anytime we want to factor something, if we can find all of the roots of it, that's the most important thing. Now, things that we have, the things that we can use to our advantage is anything that we've learned with algebra up until this point. So that's kind of nice. Now, negative 3 minus I is a complex root. Something I want to mention about complex roots. If the given polynomial has real coefficients, and r equals a plus bi is a root, then the complex conjugate is also a root. Then r equals a minus bi is also a root. That's a couple things we're going to be using to our advantage here. If a given polynomial has real coefficients and you have a complex root, then the complex conjugate is also a root. Now this one takes the form a minus bi, so a plus bi will also be a root. Big important thing for us in this problem is that negative 3 plus I is also a root. So in response, I'm going to set up a little synthetic division table. Now for synthetic division, in the upper left-hand corner, we put whatever root we're using to divide. Let's start with this negative 3 minus I. Negative 3 minus I. And to the right of this, go the coefficients of your polynomial in descending order. So we start with x to the fourth, that's a 1, x cubed is a 4, x squared is a 3, x is 10, and then constant term is 50. Got a little bar going on underneath that, and we'll set this aside for now. Alright, so setting up our synthetic division, we do have a complex number, so some of the numbers might get a little tricky, but it's nothing we haven't seen before. Negative 3 minus I times 1 will be negative 3 minus I. If I add up the column, 4 minus 3 is 1. Nothing to cancel with the minus I, so we'll get minus I. Next, we do negative 3 minus I times 1 minus I. I'm going to bring in that extra piece of paper here for a little bit of FOIL action. Now, technically speaking, if your teacher is awesome like I am, they will allow you the use of a graphing calculator, and graphing calculators can multiply complex numbers for you. But since I'm feeling hardcore today, I'm going to do it by hand. So we'll recognize that I squared is equal to negative 1. We'll call this negative 4 plus 2I. That goes right up here. Yeah. Alright, we'll need to reference back to that in a sec. So 3 minus 4 gives us negative 1. And then plus 2i gives us plus 2i. Alright, next up, negative 3 minus I times negative 1 plus 2i. Let's go right back to this. Negative 3 minus I, negative 1 plus 2i. Let's see. Negative 3 times negative 1 is 3, minus 6i, plus I, minus 2i squared. Alright, that's going to require a little bit more work, so I squared is negative 1, so this will be 3 minus 5i plus 2. So it'll be 5 minus 5i. That goes right up here, 5 minus 5i, and we repeat the process. Add up the column, we'll have 10 plus 5 will give us 15, minus 5i. Now at this point I like to cheat a little bit. We know for a fact that this is a root. We know it's a root because, well, because I say so. That'll work. When I multiply these two things together, I'm supposed to get something that I write up here. And when I sum the column, I am going to get 0, because we know our remainder is going to be 0. So when I do multiply them, the answer is required to be negative 50. It's a little shortcut you can use as you're working through the process. Now this is only if you know for a fact that it is a root. So, you know what, just to be safe, let's go ahead and confirm it. Let's do 15 minus 5i times negative 3 minus I, and confirm that we get negative 50. So 15 times negative 3, 15 times negative I, negative 5i times negative 3, and then negative 5i times negative I. Notice that the inner and outer terms cancel out. Our I squared over here becomes negative 1, and we do in fact get negative 50. I'm feeling pretty good about that. You should too. Sweet. Alright, so that takes care of our first synthetic division. Now we are going to need a follow-up synthetic division. We know that if negative 3 minus I is a root, then negative 3 plus I is another root. So first off, I want to partition off that 0. We don't really care about the 0 anymore. What we care about is this polynomial. So let's repeat the process. Also, the multiplications are going to be a lot easier this time because all of the complex parts should drop out. Negative 3 plus I times 1 will be negative 3 plus I. When we add them up, the complex parts do in fact cancel out. We'll get a negative 2. Negative 2 times negative 3 is 6. Negative 2 times plus I will be negative 2I. Add them up and we get 5. Multiply 5 times this last bad lad right here, and we'll get negative 15 plus 5I. And indeed, that'll give us 0. So the interpretation that we can give to all of this is our remainder. Here's our constant term, coefficient of x, and coefficient of x squared. So the interpretation of the quotient, this is x squared minus 2x plus 5. This cannot be factored using the real numbers, so we're going to have to go to the complex numbers. So to find roots, we said roots of a polynomial are where a polynomial is equal to 0. Equal to 0. So we'll set it equal to 0, and we will solve. Now there are tons of ways to solve quadratic equations. You got factoring, you got quadratic formula, you got my personal favorite, which is completing the square. So that's what we're going to do. Move the negative 5 over, take half of negative 2, and square the result. Negative 1 squared, that'd be 1. That's what I'm going to add to complete the square. Left-hand side becomes x minus 1, quantity squared. Left-hand side, negative 4. Take a square root, and we'll have x minus 1 equals. Anytime we take the square root of both sides of an equation, you should see a plus or minus sign pop up. So my other two roots are going to be, simplifying square root of negative 4, that'd be 2i. I get 1 plus or minus 2i. Now, let's take that back to our previous sheet, because now we have all 4 of our roots. So, our roots... Wait, what did we just say? What were the other two? 1 plus or minus 2i. 1 plus or minus 2i are roots. So now, we're going to use what we call this factor theorem to turn all of these roots into factors. We do x minus each root, we get a factor. X minus negative 3 minus I, that was the first root given. Then we said the complex conjugate of that will have to be a root as well. Then through our algebra we also got that 1 plus 2i is a root, and 1 minus 2i is also a root. So for all of my complex roots, I put the complex roots in parentheses because that negative can distribute through. If you want to distribute it, that's fantastic. Otherwise, I would be perfectly happy with that as a final answer. Wow, that's a really bad rectangle. Regardless, I hope you found this informative, and I'll see you again sometime soon.